One issue that people run into a lot when actually designing spaces with speakers in them is that sometimes you run into dead spots. And we can actually look at just the standing waves in a closed, room just by looking at these three dimensions here. These are the dimensions of the room. They didn't tell us which is the length, the width, or the height, but it doesn't really matter. We're going to just treat them as basically closed. I mean, it's a closed room, so each wall is going to have to be a node, right? So just to review a couple things, a node is a point where the wave has a zero amplitude, or the standing wave has a zero amplitude. And a node usually happens in a place where things are fixed. So for example, the walls will create a node. If you have a pipe, the closed part of the pipe, or where the water level is in a pipe, that would create a node. In this case, the walls are going to be nodes. And the question is asking, for each one of these, we want to look for the standing, the fundamental frequency. Now the fundamental frequency is basically the largest wavelength, or the smallest frequency that we can create in this tube, or in this room, I guess. So the largest wave that we could create would actually be 1/2 of a wavelength, because these both have to be nodes. And so in order for them to both be nodes, this is the largest wave that we can make. Now you have to understand, we could make smaller waves, like if I put another node here, then we could do a full wavelength, but that's not really helpful because that's not the fundamental frequency, so we're not going to do that. So anyway, moving on. So the length of this here is just going to equal 1/2 of the wavelength. In fact, that's going to be true for all three of these. The only difference is each one has a different length. Now the only other thing we have to do is we have to take care of this wavelength part, because we're not asked for the fundamental wavelength, we're asked for the fundamental frequency. So that's where we're going to use the wavelength equation, or the wave speed equation, which says that the speed of the wave is equal to the wavelength times the frequency. And we want to substitute the wavelength for the rest of this. So we're going to actually solve for wavelength. I'm going to divide both sides by frequency, so I get speed divided by frequency. So the equation is going to be, if I substitute this whole thing in for wavelength, I get speed over frequency. So now I want to solve for frequency. So the way that I do that is I multiply both sides by frequency. That's going to cancel that out. So I get frequency times the length is equal to 1/2 times the speed. And then I want to get frequency by itself, so I'll divide both sides by L. And so I get 1/2 times V over L. So let me rewrite that down here. Frequency is equal to 1/2 times the speed divided by the length of the pipe. Now the speed of sound is given in the textbook as 343 meters per second. That's the speed of sound in air at normal temperatures. So the frequency, I'm going to rewrite this over here, is equal to 1/2 times 343 divided by the length. And now this equation we can use for all three lengths. We just plug in each length and solve for the frequency each time. So let's go ahead and do that. So we have 0.5 times 343 divided by the first length, which is 4.7. So I'm just going to write this out. So 1/2, or 0.5 times 343 divided by 4.7. And that's going to give us a frequency of 36.5 hertz. I'll round it to there for now. And then the next one, 1/2 times 343 divided by 3.6. Put that in the calculator again. And I get a frequency of 47.6 hertz. And then the last one is 1/2 times 343 divided by 2.8. And when I put that into the calculator, I get 61.3 hertz. So these are the three fundamental frequencies. And if we're given 2 sig figs, so we should actually put these in 2 sig figs. So this would round up to 37 hertz. This one would round up to 48 hertz, and this one would round down to 61 hertz. So these are your answers for the 3 fundamental frequencies for each dimension.